I see some faces with whom I've been in the mud and rain in the past. Always very comforting to know you're here to bail me out as you've done in the past. Today we're going to talk, I see you had a theme of ecosystems. So the title is Ancient Ecosystem and Arrows. I would like to point out that I was going to be co-presenting today with one of my students, and I was an advisor to her PhD. And it's because of her that I've gone around Trinidad looking at some rocks. We're going to talk a little bit about today. It's a shame she couldn't be here. She called me on my way to pick her up in Maraval to announce that she just tested positive for COVID. So I'm sure, while you regret her absence, you're glad that she's not here. Well, I'm glad she's not here. And that she bothered to test before she came. Okay, so a couple of house rules. Just remember to turn your phones off. It might be convenient for others to not have your phones going. And the other house rule is to ask questions. What does everybody see there? What is this to anybody that's... It's an arrowhead, is it? Yeah, okay. Well, that's the example, that's the answer I expected. But to me, it's a piece of chert. Okay? It's a rock. It's been shaped by man, but first of all, it started its life as a rock. The rock is unique because we can make arrows with it. It is one of the few rocks with which humanity, made hunting tools. And it's unique because, you see, this cuspate fracturing leads to a very sharp edge, which is what you want in an arrowhead or a knife or a spear. If you want to kill people, deer, antelope, or whatever it is, those are the characteristics you need of a rock because they didn't have steel. Okay, so to me, it is just a brown piece of flint that man has hit with another piece of flint to create a shaped piece of rock, but it's still a piece of rock. And we're going to investigate the history of this piece of rock and why it was used and how it came up to be a rock that man has used or had used for millennia and is found and is cherished by ourselves as artifacts that we find in the field. The size of the rock is quite impressive. I mean, it's quite a big arrowhead. It's a centimeter bar scale at the bottom. And it was found in Trinidad in a midden for indigenous people. And the rock is made of something called chert and or often called flint interchangeably. Okay, so what is the outline of the talk today? We're going to talk a little bit about something called plate tectonics. And I know I've talked to you a little bit about that before and in the past, and most people are probably aware about it. But it's thanks to plate tectonics and the reconstruction of how the plates on the planet have moved that we know where Trinidad's place is in the world now and in the past. So we are going to contend that this arrowhead, this rock flint, is a product not of volcanoes or anything normal, but it is a product of a unique ecosystem which produces this unique rock which has provided mankind with this hunting tool or knife for millennia. And that's what we're going to explore a little bit today. And we're going to look at where we can study that ecosystem and what the rocks tell us about that ecosystem. We're going to see what the rock really looks like, what the rocks were used for, and then we're going to have a summary at the end. So don't forget, you can ask questions. Okay, I need to acknowledge a lot of people to get to this, to be able to give this lecture. Hans Kugler, who created a geological map of Trinidad. There were many before, and there have been some since. But that's the map I'm going to use throughout the presentation. A guy called Jack H. Ray, who wrote a paper on the use of chert by indigenous peoples in Trinidad. I will be able to give you that reference should you want it. A guy called Bob Ehrlich, actually his real name is R. Ehrlich, but I refer to him as Bob because we've been friends for years. And he talks about the paleo environments that we're going to see from the period in which those paleo environments occurred in Trinidad. A guy called Gene Raw, good friend of Reg's here, and he did a lot of work on how Trinidad moved through time, which we call reconstructions in my Hazley Vincent, John Webber, that was mentioned earlier because I worked with him quite a lot, and I've worked with him on some of the stuff you're going to see today. A guy called Scotties, who has reconstructed where the plates have been in the world, and therefore where Trinidad was, and where it went, and where it came from. Jim Pindell, who did the same. Chantelle Hughes, who's going to be the co-presenter, and lots of other geologists and paleobotanists who have helped us understand how these rocks were formed. So, map of the world, just as reference. North America, Trinidad, the red dot, South America, the rest of it. The black areas are areas where earthquakes occur frequently, and ones of large magnitude. Once you make that observation, you realize that in the areas between earthquake centers, there are very few earthquakes, and where we lie is on a belt of earthquakes that goes around like this. And it is plate tectonics that creates the atmosphere, or the correct conditions for earthquakes to occur. So these are just events that we've been able to map worldwide between 1963 and 1990. So the world is made up of these things between the earthquake bands that we call plates. And they're plates that move internally together. Sorry. Oh, this is Trinidad. Sorry, not very clear map. This is Trinidad, northern Trinidad, southern Trinidad. And you can see that that belt that comes across here extends across northern South America and through Trinidad and off into the Atlantic. I'm going to separate, for the rest of the presentation, I'm going to separate Trinidad into two areas, a purple area and an orange area, for the sake of simplifying what is going to happen to the place. So, based on those earthquake epicenters, I'm trying to find a map that's not really that similar, but trying to be similar. And we put between, these are the earthquake bands, the red lines, we put in between them names of different plates. And here, you can see Trinidad, and it's on the southern boundary, and I'll also show you on the northern boundary of the South American plate, on the southern boundary of what we call the Caribbean plate. Here's the Pacific plate, this is the Atlantic plate. Okay? What does that mean to us? Well, again, here we are. It's a big map, it's a big world. And today we are here. The question is, were we here through geological time? And I'm hopefully going to take you on a journey that is going to show you that half of the island has been here for a long time, and half of it has not. Thus the color boundary. Okay, so here we are, the orange part of Trinidad, the purple part of Trinidad. This plate, so that's a unified blob of rock, is moving this way. This is the mid-Atlantic ridge. This side is moving this way, this side is moving this way, and the junction between this and this happens to go through Trinidad at that plate boundary, which makes us particularly prone to earthquakes. The Pacific plate is going in under that. So just to give you a feel for the differences between there and there, this is the Caribbean island arc, so that's the volcanoes that go up here. Here you have this plate going under and melting, and the volcanoes are a product of that. And this side is coming this way. So this is being subducted, we call it, and that's going under, melting at about 180 kilometers, and the melted product shoots to the surface. On this side here, all we have is a continent on this side, and nothing much is happening as we just get into the deeper and deeper ocean. This we call a continental shelf, continental slope, and a continental margin. What I'm going to try to explain to you is as this passed by, it created two very different environments. It turned out because this continental margin actually is under the purple, and everything under the orange is a bloody mess. Sorry. It's a pretty map. It shows the island arc here. These are the islands. Under this orange stuff. Orange stuff is generally, let's think of it as a mound of rock. Here you've got the continental shelf that we showed. And while this does no longer extend straight into Trinidad, it doesn't extend into Trinidad only because this big blue deep hole, this is like a swimming pool here, one of the deepest crustal holes on the planet, has accommodated the Orinoco Delta as it's pushed the rocks down. I put a line through Trinidad here, separating the north of Trinidad from the south of Trinidad. This would be orange in my reconstructions. This would be purple. This went like that. This cut that off and left us with the northern range coming from somewhere, which we're going to try to reconstruct through time. So this is kind of Guyana, and this is the southern end of the Orinoco Delta. To give you a reference. Put in more geological terms. Here's my red line through Trinidad. This would be orange, this would be purple. Here's the delta. This part is going this way. This part, you can see from everybody's arrows, is going that way. The pit that's going under has squeezed all of this mud and dirt up to the point where you get Barbados here, which is squeezed up mud in front of the volcanic arc, which is going that way. Okay? And in between, at the boundary between that part going this way and this part going that way, it's pretty messed up. And that's caused, these are faults, and the faults are caused by rocks shearing and breaking like glass. So, but it's not, okay, this is going to make a suggestion that it's not that simple. Maybe it's not that simple. But what we can do today, which is amazing, is that GPS work is so accurate, if you really try to make it accurate, we can actually measure how fast Trinidad is moving in a given direction at different places on the land. Okay, so I can actually measure something that is moving at the rate that your fingernail grows, which is what we're talking about in terms of plate tectonic speeds, using GPS. It's not almost an incredible amount of accuracy using satellites, and that's what we can do. Okay? So we can actually put stations, and each one of these arrows represents a station that is on Trinidad, and we can tell how much it moves every year by measuring its GPS location year on year. This isn't a hypothesis. We are now actually making measurements of the speed at which Trinidad is traveling east. Okay? I told you that they were doing this, but that's a relative speed. So you could be doing this, but moving this way all the same, as a plate, as two plates, right? So relative to each other, they're doing this, but they're actually all going towards east. And these arrows depict the measured speed on a scale, the measured speeds at which these are going east. Here at this dot, it's not moving at all. Okay, so we get zero movement here. We get relatively increasing velocities as we go east towards the north. And we draw a line through here because we think that the orange area and the purple area were approximately moving this way, or relatively this way, but that way altogether at the same time. So the absolute speed here is a function of the fact that this is actually going this way slowly, and that's going that way fast. Okay? Sorry, I went the wrong way. All right. So, to find this ecosystem that created flint, we have to go back a long way. You guys saw Eocene rocks in the field and you said 60. We're back a little further than that. We're going to go back to about 65 million years ago. And to give you the atmosphere of what things were like, the great Cretaceous extinction had not come about yet, and the land was the domain of dinosaurs, and the king of the sea was a thing we call an ammonite, which is kind of an octopus with a shell, or even better, squid with a shell. And they don't know why they chose to make the shell a spiral, but I think it was to do with hardness and difficulty be chewed up by prey. Okay? But that's what they look like. So, in the grand scheme of our planet, which is like a clock here, where we are here now, we're only going back a tiny amount. We're not going back to 1145, which is 65 million years ago, because this is 4.2 billion years. So we think the planet became a planet. We can start measuring its age from 4.2 billion years ago. And that's about halfway through the life of the sun. So if you really drew this map, in terms of our sun and our solar system, we would be at 6 o'clock in the grand scheme of time. So we're halfway through evolution, as we know it, on the planet. Life began about halfway through this time scale. And since then, it's been evolving. And we have various periods. The one we want to talk about is the one that's about 65 million years ago, which is when our ecosystem developed. And this demonstrates how far life forms had developed then. Through most of this, we have no record of life forms at all. So back to Trinidad. That's my red line that I drew. And this is a Kugler map. And the north half of Trinidad is orange, remember? And the southern half is in purple. And it was attached to South America through its whole life. Through up until quite a long time ago, 300 million years. And we're familiar with the northern range sediments, and they're very different than the rocks that are found in the rest of Trinidad. Just go back up. Forget what the rocks are, but you can see that the color schemes used by Kugler for the northern half of Trinidad are very different than the color schemes that he used for the southern half of Trinidad, because the rocks are different. And I'm sure you are familiar with different rocks in Trinidad, the Laventille Formation, which is where we get the beautiful building stones that we have lost. The Gunapo conglomerate, which you find around Tuku. The Galera grit, which looks a lot like Mount Harris rock that you saw, but it's very different in many different ways. And you guys know better than me that the whole atmosphere and the way plants grow and behave in response to the climate and the soils is very different in northern Trinidad than south and central Trinidad, in my view anyway. So, late Cretaceous. Cretaceous really means limestone in a different language. So it's a period when there was a lot of limestone. And chert, or flint, remember that's this magic material that we're trying to find, because people needed it for arrowheads, has been described. San Fernando Hill, Ben Lomond Quarry, Chert Hill, inaptly named, but we'll call it that, and in a few wells in and around Trinidad. This is the La Brea area, this is Rock Dome, actually I'm not sure I put it in the right place, and Guayabera. Okay, and we sit all in the purple part of the map. So San Fernando Hill, what do we see there? Well, San Fernando Hill is a pretty outstanding piece of rock, isn't it? It's pretty hard. Otherwise it wouldn't be sticking up like it is. And what is it? Most of you are familiar with the fact that it was intensively quarried. Because in south, they didn't have many hard rocks, and they needed to make roads through the cane fields and later in the oil industry. So it was beat up pretty bad, which gives us a chance to see it. But it is a hard rock, and it's hard enough to be used as a poor road metal, but it's very, very quarried. But it's an outstanding monument to the Cretaceous. The Cretaceous, we will look at a bit more because it is where our ecosystem is going to occur. So what I want to do, and I want you to focus just on the orange and the purple. The purple is South Trinidad, the orange is North Trinidad. We're going to take you through a little journey in time, built by this guy called Hughes, showing what's happened to the different parts of the planet at different times. And I'm going to focus in on the Caribbean plate. This is our red stripe today, and you can see it lines up with this orange line that circumscribes what we call the Caribbean plate. All right? The equator is down here. Bear that in mind as a reference. So we're going to go back just 14 million years, and you can see that our purple bit of Trinidad has been left behind, or looking at it the other way, this has traveled this way through time because it's going at a different speed, and is now back here. Importantly, for all of us that are interested in paleobiology, there was no closure to the isthmus that links, that blocks off that side of the Caribbean plate now. So that we know that there was oceanic flow through here, and the Atlantic and the Pacific joined, without having to go to very northern or very southern latitudes. So we know from the diversity of the species and how they work, they were similar. Now, because the equatorial land bridge, the fish's Panama Canal, if you like, wasn't there, fish could swim across and therefore breed and therefore have similar genetic, similar genetic. The equator is not moved. Everything here is more or less moving east-west. We're going to go to when your growing rock occurred. You can see that by now I have moved the northern part, or Scotties has moved the northern part of Trinidad further to the west, because it's continuing to travel this way. So if we take back time, it has to be this way. And you can see that the Caribbean plate didn't exist at all. Okay? This was just an open seaway with a few islands, but we had no island arc forming in this part of the Atlantic Ocean. So we were basically in the Atlantic Ocean with no barriers, and we were no different than the whole of the South American shelf that was all through here. Trinidad at that time was part, the northern part of Trinidad, was at that time also part of a shelf. And it received the sands that you saw at Mount Harris. Now we're going back to where we want to be, which is when our ecosystem is going to occur. Two things of major importance happened at that time, which are responsible for this unique ecosystem. Because there are very few, if any, flints or cherts anywhere else in the rock column of Trinidad. So remember, the purple part was just on a continental shelf. Sorry, this is the wrong way around. The purple part was here, this is there. This was way around the corner now, almost where Colombia is now, and it's going to shoot around in time to end up here. Back then it was there. But this was just a very quiet, no rocks, no big tectonic events, no problem, nothing. It was very, very, very quiet. And we were just part of the entire shelf that stretches through here, which, by the way, the rocks of this age are what they're finding oil in up here now. Okay? So, anyway, we can deliberate about that another time. But again, you see there's no Caribbean plate at that time. The plate boundary came straight down this way, straight down South America, formed the Andes. And the north part of Trinidad was right near where the Andes was, which explains why it's a much more messier series of rocks at this time. I mean, lots of gunk in it, because there were huge mountains near it. The other thing that you'll notice about the Cretaceous is because we know that these two are pulling apart. Can you see how narrow the South Atlantic is? Completely different than now. We're spread a huge distance apart. And you can see one of the major events, which if you put into current world climate concerns, sea level rose by a long, long way. And it flooded huge parts of the shelf, including all down this trough of South America. This was flooded back a long way. You can see that South America has a funny old shape here because this shelf was flooded because sea levels rose, and they rose by a lot. And I've seen estimates of temperature rises that led to that sea level rise of 5 degrees. Okay? So hot, and Trinidad would have been in relatively deep water because sea level rose, not the shelf. The shelf didn't go down. And that meant that all the rivers that might have fed into Trinidad, being near the coastline, were further back, and therefore Trinidad was relatively starved of sands and coarse material. I thought I'd go back a little bit further so that you could see that this is the southern Atlantic, completely closed off. Trinidad was either part of Africa or very near to it. We're no longer in the sea, we're actually on the land, and you can see that the Atlantic is opening up, and we were very close to Houston, Louisiana in those days. So that sea, this Proto-Caribbean Sea, was very small. And if you go back to the early Jurassic, which was about 195 million years ago, so double the numbers that we're talking about, Trinidad sat in the middle of a big, hot, single continent that covered a piece of the planet, and all of the big continents we know now will join it. Okay? So, what do we have in our Cretaceous? In the purple part here, we're on what we call a continental margin. Just very calm, very passive, part of the North Atlantic. The plates are moving in all kinds of directions. We don't have a Caribbean plate. Our red line has disappeared because there's no fault here. This is out here somewhere and hasn't arrived. And the plate that's going to bring this here hasn't really developed yet. And we know that sea level flooded most of the area, so we didn't have many rivers and streams bringing sediment into Trinidad. This curve here is the ages that we described. Time is here, I'm not sure you can read that, but that's up there. This is reading up. No, this is time. I can't see it from here. But this is 65 right here. So this is 100, that's 50. This must be 200 if you can read it. What I'm trying to show you is that this is called relative sea level. It's not an absolute measure of sea level, but it's trying to give you an idea of when sea level is high versus sea level low. This side is high, this side is low, and you can see that the Cretaceous is a massive anomaly, where the sea was higher during the Cretaceous than it's been for the most of the geological history of the planet. So it was a very different time. From a sea level point of view, it was unique. Almost. You might argue that this was as bad. So very special conditions that led to our flint chert. That's a picture of bioluminescence on a beach. And now we're going to talk about the ecosystem that occurred at the time to create our rock. Oh damn, I'm doing it again. Get rid of that. Help me. Thank you. Page down. Gotta hit the right button. Okay. So bioluminescence, I'm sure you're all aware, is caused by plankton. Plankton are amazing little creatures that are either zooplankton, in that they eat other plankton, or they're phytoplankton, and they use the sun to grow. They photosynthesize like any moths and things, and they're called plankton. And what is beautiful about them is they've got the most extraordinary shapes. I mean, they just come up and they really have it from a geometry point of view. They ain't nothing like plankton in my view. So these are some of the shapes. And here are some other shapes. Anybody know that there are Well, there are two types of plankton, basically, like I said, phytoplankton and zooplankton. Zoo being animals, the other ones being phyto, as in photosynthesis. But there's another classification of plankton which is very interesting and much more interesting to us geologists than whether they were animals or plants, is they use two different kinds of materials to make their skeletons. What do we use to make our skeletons? What are our skeletons made out of? Huh? Sean might know. Calcium, right? And what anybody got any idea what plankton use as the other thing that they use to make their sharks use collagen, which is not calcium based, but then we're not talking about that.
Silica.
Silica. Yeah. Silica. So these guys have bones or skeleton. It's made out of silica. So they can capture silica from seawater and turn it into a skeleton. And others capture calcium carbonate, just like corals do, and they turn calcium carbonate into their skeleton. So if you pick up a batch of plankton, within them there will be skeletons made of silica, there will be skeletons made of calcium carbonate, and the other thing that's in them is organic material, carbon-based molecules of different types. Okay? That's the three things that you get if you basically crush plankton into its basic ingredients: silica, calcium carbonate, and organic matter. There ain't nothing else there. Okay. I put some pictures up of what we call siliceous planktonic radiolaria. And again, I think when it comes to geometry and building stuff, they're unbeatable. Okay, so all of the dark stuff in these slides is silica, all of the white stuff is holes, and those are their skeletons. Okay? I'm talking of dust-sized stuff, plankton. I'm not talking about, we're talking dust. If you take this and it's dust, I just want you to get that in perspective. All right, but I think you can admire the different shapes, different ways of building structures. And then we have calcium-based skeletons, and these were very used in Trinidad's Trinidad's geological record. These are fossils. But I want to point out that while these are spirals, like a snail, of calcium carbonate, inside of these is empty and hollow. So again, you're dealing with a thin skeleton, animal inside, photosynthesizing or not, but very thin calcium carbonates. These are nanoplankton, which are also made from calcium carbonates, and they're just there to show you that things are small or very, very small in that world. Okay, so what is the ecosystem in which these animals are formed? And here are organic matter plus skeletons. First thing they need is lots of nutrients. So you have to be in a place where silica and calcium carbonate can occur in enough abundance. You've got to have sunshine, you've got to have reasonably clear water, but you've got to have nutrients. You want to have a lot of this plankton. Okay? Trinidad currently has, and we will try to show you that Trinidad must have had quite a high bioproductivity on the continental shelf. So what happens to these when they die? Well, calcium carbonate is one of the weirdest minerals one of the weirder minerals I know. It's weird because it actually dissolves in colder water under high pressure. I'll give you an example. When you boil your kettle, calcium carbonate precipitates, right? When you put sugar in your boiling water, it dissolves. Okay? So it doesn't do what you take salt. Put salt in boiling water, it dissolves more and more the water is hot. calcium carbonate is different. It comes from cold water, where it's dissolved, and it comes up, and it's stable, shallow. And therefore it can be used to build skeletons in shallow water quite easily. I mean, you don't want to make your skeleton out of something that dissolves at the surface if you're trying to use the sun to make energy. So that's one of the reasons that it's used in skeletons. But so in that way it's quite different. And when you get to deep water, below what we call the CCD, which just means the depth or the temperature at which calcium carbonate dissolves, all of the calcium carbonate in this mixture is going to dissolve. It just can't, it's so fine, it's so fragile. Any ability to dissolve is going to take it out of the water column. And you're talking about dust in the water column, You're not talking about things that are dropping like a stone. I mean, I've seen some studies that say that if the calcium carbonate is not incorporated in fish shit, it never gets to the bottom because it's so fine that it keeps circulating until it dissolves. Okay? So we have to be so that dissolves. But the silica does not. So if you have a mixture of calcium carbonate and silica, and the water depth is deep enough for the water to get cold, it's only the silica forms are going to get to the bottom. And they're going to get there with organic matter. So organic matter stays, silica stays, calcium carbonate may or may not stay. Okay, but we use that calcium carbonate depth as a definite water depth indicator. So if you have a sediment that has calcium carbonate, it can't have been very deep. If it's pure silica, therefore flint, it was deep. Okay? So, decomposition, because organic matter starts to dissolve, decompose, and the solution is taking place all the way down the water column. And then it hits the bottom, which is where our pirogue is anchored. And after that, it goes through a number of changes again. Remember, those fossils are very, very, very fragile, very, very, and full of water and full of organic material. So it gets squeezed. And when it gets squeezed, that's when silica starts to behave badly. It dissolves. It's not very stable once it hits the sea bottom. Starts to get squeezed, starts to get to higher temperatures, because as you go down, temperature increases, and it starts to change. We're expelling water, which there was a lot of. We're expelling oxygen, and the expulsion of water and oxygen helps preserve the organic matter. So if we're lucky, by the time we're a few feet from the sea bottom, we have organic matter in a very low oxygen, because all this organic matter is getting eaten up on the sea bottom. Water is being expelled to help preserve everything, and oxygen is being expelled, which helps preserve everything. So if we're lucky, when we get past here, we've got silica, some calcium carbonate, lots of organic matter, some iron and some magnesium. Things that were big and circular at the surface get squeezed until they become flat like rice grains, if they were sphere. Okay? And through here, what you get is an increase in temperature. I mean, we know that the core of the Earth is molten, and we know we can walk on the surface. So there has to be temperature decrease as you go from the core to the top. Invert that, and as you go down, it gets hotter. Okay? So that heat causes all of these to go through chemical changes, and at the end of it, we're going to end up with either chert, limestone, and the organic matter is going to convert to oil. Alright? So that's what our plankton gives us. So let's have a look at what limestone looks like. This is 100% calcium carbonate. That means that we had, because of the ecosystem, not enough silica in the system to get in it. Mostly calcium carbonate precipitation or productivity, and it's grown into layers like this, and this is what it looks like. In this example, 100% calcium carbonate. What we call flint or chert looks like this. So we've taken those tiny little powdery grains of silica skeletons, and through change occurring because of heat mostly, it ends up being this kind of glassy but very fine-grained rock. And you're beginning to see the characteristics in that would make it a good rock to have sharp edges. Yeah? See how it breaks in like glass? And that's what the people wanted. They wanted something that broke like glass so they could get sharp edges. Just like glass has sharp edges. What other materials have sharp edges like that? Not many. Because you need that very, very fine-grained rock that will then break in what we call a conchoidal fracture. And this is an example of what we typically call flint. And that's an example of what might be called chert. But to get these characteristics, you need a very high percentage of silica preserved. And that's not common. Okay, so only a very unique set of circumstances will create the rock that you can make arrowheads from. So let's look at some examples of those Cretaceous rocks at different localities, or mostly at San Fernando Hill, that we said are localities in which the rocks are described as cherts. I'm sure most of you have visited San Fernando Hill and have seen large white slabs of rock like that, which have lots of fractures. This is a hammer for scale, and we think of it as a white rock, yeah? It's white. You can't lie about it, it's white. And it's got lots and lots of fractures. Okay? And it is quite often called, Mr. Kugler called it an argillite, which is probably the worst descriptive term for that rock, but it's a misnomer to call it chert. It's a silicious limestone, as I've put up there, which means that it's not pure end member of either a limestone or another. What it tells you is that because it's got limestone, it was above that calcium. First of all, both products are being produced, calcium and silica radiolaria, and they were being preserved through the column. They hit the bottom, and therefore you've got a mixture in these rocks of both silica and calcium carbonate, and therefore, because it's not pure chert and it's not pure limestone, it's called a silicious limestone. See, as I told you, it's quite fractured, it's in layers, and this black stuff coming out of it is coincidentally oil. And San Fernando Hill is absolutely inundated with oil. In other parts of the world, where the name Cretaceous was invented, this very white rock here, very fine-grained white rock, is called chalk. And the French word for chalk is cret. And therefore, the Cretaceous is why we call it the Cretaceous, because it's a time at which there was a lot of calcium carbonate, fine-grained calcium carbonate precipitated. And what happens to the small percentage of silica is that it becomes concentrated in what we call nodules. So you see these black nodules. And because the silica has been dissolved out of all the chalk and formed in nodules, due to local chemical changes in the rock, these are called flints. With a white exterior, very dark interior, and it breaks like glass. But these rocks are not busted up. Our Trinidad rocks are pretty busted up because we've had all that plate movement squeezing and wrecking the rocks, and therefore we have cracks through these rather than it being a nice smooth rock like this. This is what people in Europe used as their primary source of arrowheads. In San Fernando Hill, and not very well recognized, is that within the white rock, which is all here, we've got these patches of very black rock. You see the outline here? And this is 100% silica. These are nodules that are formed by dissolving the little animals, and they coagulated because local chemical conditions cause them to coagulate, and they form these large blocks, or nodules as we call them, of black material. which we call chert. That is bona fide chert. That is 100% silica. And if you can see from back there, you can see it's pretty busted up. These are veins and stuff. But you can see there's some nice little chunks. This is a scale of an inch. This is about an inch long chunk, a bit bigger here, a bit bigger there. And these chunks, when they rolled off the hill eventually and got into rivers, might be blocks of a decent size, from which it is clear that the we'll show you why the Amerindians use those as very important tools in their arsenal to eat and kill others. This is just oil seeping off from San Fernando Hill. I don't know who the young man is, but it's been a few years ago.
What is manjack?
Manjack is it's an organic. It's oil or like an oil that hasn't really got to the stage of being oil yet. So it's a very high density wax. It's a wax, and it was used for insulation because it could be machined, and it's got great insulating properties. And it was just like a plastic. It wasn't quite. If you take manjack and you heat it up and stuff, you'll get oil. But it is organic material. It's just been heated up a little and not enough to go to oil. But not organic material anymore either. Okay, next. So, in Trinidad, if you walk around Central in particular, not far from places where you get names like Chantelle or San Fernando, you find in the rivers rocks that look like this. And this is a pebble that I picked up in maybe Mayo Quarry, because there's a pebble bed there. And you see that it's zebra stripe. The white part is more limestoney or more calcareous, and the dark bands are more siliceous. Okay, so in detail, these rocks are a mixture of, like I said, silica-rich, then periods when it was more limestoney-rich, then periods where it was more silica-rich, and periods where it was more limestone-rich. But there's enough silica in this rock to make it have these relatively sharp edges and this kind of fracture that gives you the feel that I might be able to break this rock and use it as a sharp edge. Okay? And that's all they wanted, sharp edges. They didn't have steel. And in Trinidad, there's a real dearth of rocks that you can make a sharp edge with. So if you look at these pebbles in the rivers, first thing I like about this slide is that when you break the pebbles open, they're white on the outside and black on the inside. Okay, remember San Fernando Hill was white? If you break the white rocks, they're actually black inside. So, yeah, the white is only skin deep, as they say. So this rock here has been altered. And one of the things that we think alters those rocks is bacteria that are sulfate, what we call sulfate-producing bacteria. They use the remnants of the organic materials left in the rock, attack it, and because it's sulfur-rich, it's calcium sulfate, and that coats the outside of the rock. You get a white rock and a rim inside, on a rim, a white rim on the outside with dark rocks in between. So don't be fooled by a white rock. In Trinidad in particular, break it open and have a look at what's on the inside quite often. As you can see, these are all pebbles that we've broken. Some have not gone white on the outside, but certainly some have. And sometimes the skin is thin, and sometimes it's thick. Okay? And what I want you to see from the texture of these rocks is that they are prone to flaking and having sharp edges. Okay? So if you go to places where these pebbles occur, two things you notice is that the amount of more churty looking rock is much higher than if you went walking around San Fernando Hill. I'll explain that in two ways in a bit more detail. But what happened, what we've noticed, is that more you have silica in the rock, the more it has the ability and the quality to make quality tools. So 100% silica, great. As you go towards more and more calcareous rocks, the sharp edges and the correct fractures are lost. So we're looking for chert. And the Amerindians look for chert real hard. And the place that I found the most chert, and I'll show you that others have found the same thing, is actually in the pebbles of the Central Ridge. And that's because limestone dissolves in rain. Okay? They dissolve in water. And that means that anything with a lot of lime in it dissolves faster than anything that's pure silica. So if you actually let weathering do the work of sifting out the hard rocks from the soft rocks for you, you actually end up with more hard rocks. And the hard rocks are the ones that make good tools. So there's kind of a sorting process occurred there. The Amerindians figured that out, and we will show you. And you know, you can see it here. These rocks are pretty sharp-edged. It's another example of a sharp-edged rock. So this would be high in silica, and rocks in most of San Fernando Hill would be lower in silica. On the surface of some of these, the silica content is so high that it's redissolving and it's forming an opal skin surface. And you all know what opal is, right? It's the same thing. It's pure silica, and it has iridescent coloring. Okay, so this is on the right. These are discovered arrowheads, spearheads, whatever you want to call them, in Trinidad. And these are other tools that they found in the Middens. And those tools seem to have mostly been used for skinning animals, scrapers, knives. And apparently they use those things a lot embedded in wood as scrapers of manioc. Yeah? Which was a scraper. How do you find something that's sharp enough to break the manioc down into usable farine and the juices which they made beer from? They use these shards from the rocks here to assist in that. And what is amazing is that as people learn how to use the flint here, they found that over time, the flaking method, as we call it, has changed. So there are different ways, different shapes that they made the stones into, and different ways of flaking them. So they found techniques to make very intricate and detailed sharp edges of different profiles to suit the need of what they wanted the arrow to do. And so you need to have this really high quality silica to be able to do that. So, what's the proof is that they're putting, so the guys from, that guy I mentioned earlier, his name is Jack Ray. He did some studies where he found siliceous rocks at different sites in Trinidad. This is the porcelainite areas. This is a mud volcano that has erupted and brought up rocks of this age. Remember, there's a well here I showed you earlier on. So they know that they found rocks down there. No, this is a quarry that I'm going to show you just now, which is where the pebbles are coming from, and this is the famous Chert Hill, which has no 100% chert. It's all a siliceous limestone. Am I taking too long? Yes? Boring you? Yes? Okay. So this particular quarry, which is called Malchan Hill. I don't know if any of you have visited it. Anybody ever been there? No. Well, I think it was probably an illegal quarry that was cut in the hills. Where is it? It's. I'm going to try and remember. Just give me a second. It's actually not far from River Hill. In that sort of area. I'll come back in a minute. Anyway, this is a person for scale here. And this thing is one big face of pebbles looking like this. And you can see again that this guy, this is his picture, broke open the pebbles, not fooled by the fact that they look white or beige on the outside, and he found these very black rocks, which he then decided to go and compare with what he found in middens throughout the island.
Where is Mount Chantelle?
I was just speculating that it was somewhere near. Oh, I know exactly where it is. Four Roads. Four Roads. You know where Four Roads is? No. Four Roads. Jesus. South of Tobago, a long way south. No, not south. No, not south. Tamana. Thank you. On the way to Tamana. You're right. I was just trying to have a picture in my mind. I can't get it. I can give you the coordinates anyway if you're interested. But anyway, what he did is he broke open the pebbles and he found a lot of high quality chert. And he compared that chert to other sites in Trinidad and found that what he found in the middens were lots of little flakes that he assumed were being used as scrapers and things that are used for grating manioc, cassava, and an arrowhead. So I hope that this little walk through time and space has proved to you that unique ecosystems were needed before arrowhead in Trinidad. That's it, Dave.